Welcome back to our heat transfer class, where we are delving deeper into the complex phenomenon of convection heat transfer. This video was made with the support of InnoEnergy. In the first lesson, we have seen the physical phenomenon of convective heat transfer, the different types of convection, the hydrodynamic boundary layer and the thermal boundary layer, as well as what the convection coefficient is. How is it calculated? What are the typical values? And what is the range of applicability of the formulas to calculate it? In the second lesson, we determined how to calculate the convection coefficient for convection without phase change in turbulent regime. We saw the Nyolinsky formula to calculate the Nusselt number and how we can apply it also for non-circular ducts. Now it is time to study the equations that allow us to calculate the temperature variation of the fluid along the duct. These equations depend on the boundary conditions. Let's consider three boundary conditions: constant heat flux in the wall, constant wall temperature, and heat exchange through the duct wall with another fluid at constant temperature. We will also see the concept of logarithmic mean of the temperature difference. And for the last boundary condition, we will define the overall heat transfer coefficient. There are other boundary conditions, but these are studied at master's level. We start by defining a control volume and making the energy balance, or the balance of energy per unit of time. The control volume is the interior of the duct. This is an open system, since the fluid enters the control volume on the left side and leaves the control volume on the right side. Within this volume, there is no heat generation and, in steady state, there is no energy storage. Therefore, the input energy per unit time is equal to the output energy. As input, we have the enthalpy corresponding to the input temperature in joules per second, and the convection heat transfer rate from the duct wall to the fluid. The output is the enthalpy of the fluid at the outlet temperature. All this process at constant pressure. We add the inputs and set them equal to the output. The resulting equation indicates that the convection heat transfer rate is equal to the product of the mass flow rate of the fluid times its specific heat and the temperature difference between the outlet and the inlet. So it will be positive when the fluid gets hot and negative when it gets cold. This equation is valid for all boundary conditions, since it is simply a global energy balance between input and output. We are now going to analyze how heat is transferred by convection for different boundary conditions. Constant wall flux. This can be achieved, for example, with an electrical resistance that uniformly heats the duct on its outer surface. The convection heat transfer rate is equal to the heat flux in the wall times the area of contact of the fluid with the duct. Substituting this expression in the enthalpy balance, we have an equation to solve calculation problems. Note that the heat transfer rate from the wall to the fluid does not depend on the convection coefficient. The thing that depends on the convection coefficient is the temperature difference between the wall and the fluid. At any point, we can apply Newton's law with the local convection coefficient, the duct wall temperature at that point, and the fluid temperature at that point. Thus, we see that the temperature curve of the fluid is linear and that the temperature difference between the wall and the duct varies as a function of the local value of the convection coefficient. Let's move on to the next boundary condition. Duct wall constant temperature. The objective is to find the temperature of the fluid as a function of X, and with it, the temperature of the fluid at the outlet of the duct. To find the equation, we start by defining a differential control volume. From the energy conservation equation. Analogous to how we did the overall energy balance at the beginning of this lesson. But now, with differential amounts, with which we find the differential equation. Grouping terms. The result is a differential equation of separable variables that we integrate between the beginning and the end of the pipe. Obtaining an equation from where we isolate the final temperature. Notice that the shape of the curve is a negative exponential. The temperature of the fluid approaches T0 as the length, L, approaches infinity. Logarithmic mean of the temperature difference. Once the outlet temperature function has been obtained, we are going to look for an equation that relates the heat transferred to the fluid with the difference in temperature between the wall of the duct and the temperature of the fluid, thanks to the Newton's law. As the temperature of the fluid is variable, the temperature difference with the wall or thermal difference is not constant. We recover the solution of the integration of the differential equation, grouping terms, and combining with the overall enthalpy balance. We obtain an expression of the convection power as a function of the temperature difference. Adding and subtracting T0 in the numerator, we get what is known as the logarithmic mean of the temperature difference, and that we can express as the logarithmic mean of the temperature difference at the inlet and the temperature difference at the outlet. We arrive at an expression in the form of Newton's law, where the temperature difference between the solid and the fluid is delta T Lm, or logarithmic mean of the temperature difference. We have two equations for problems where we must calculate the final temperature. And we change the second equation for the equation with the logarithmic mean for problems in which we want to calculate the length of the duct. Heat transfer with another fluid at constant temperature. The starting point is the set of equations that we have deduced for the previous case. However, in this case, there is a fluid on the other side of the wall that is at a constant temperature. We will not make the deduction of the equations that you can find in the course notes. Observing the thermal diagram, we see that it is very similar to the previous case of constant wall temperature. The second equation gives us the final temperature explicitly as a function of the steam temperature, the fluid inlet temperature, and the rest of the parameters, just as in the case of constant wall temperature. But here, the convection coefficient is replaced by the overall heat transfer coefficient, UI, whose expression we will derive in the next section. The third equation is similar to the one corresponding to T0. However, here the logarithmic mean of the temperature difference is between the fluid at constant temperature and the fluid that changes temperature. As in the previous equation, the convection coefficient is replaced by the global heat transfer coefficient. Heat transfer overall coefficient. What is it and how is it calculated? The product of the duct perimeter and length is the heat transfer area. Equating the heat transfer rate to the temperature difference divided by the equivalent thermal resistance, we see that the product of the overall heat transfer coefficient multiplied by the heat transfer area is equal to the inverse of the equivalent thermal resistance between the two fluids on either side of the duct wall. Between the two fluids, there are three resistors in series that we can add to find the equivalent resistance. We can calculate the overall coefficient both using the inner area as reference or using the outer area as reference. If we now divide by the heat transfer area I, we have an expression for the overall heat transfer coefficient I, which does not depend on the length of the duct. In summary, when one fluid exchanges heat with another fluid at constant temperature, we have three equations. We will use equations 1 and 2 to calculate the outlet temperature when we know the length of the tube, and equations 1 and 3 to calculate the length of the tube when the outlet temperature is prescribed. In all cases, we will calculate the overall heat transfer coefficient.